So welcome everyone to this talk on end-to-end stress testing with Kotlin Multiplatform. A few words about me. I'm Oliver. I'm a developer and consultant at Infix, which is a small company based in Hamburg, Germany. My background is in ERP applications, backends, and desktop and web frontends, and I've been doing Kotlin since 2016. I've been contributing to the Kotlin libraries and the compiler, so the ecosystem, and I'm also a member of CoTest. CoTest, for those not familiar with it, is a multi-platform testing framework which has a little above 4K stars on GitHub and about 21 million downloads a month, all artifacts counted. So I'd like to start with the question, which is the type of bug we hate the most? And I'd say it's the spurious one in the wild, the intermittent fault in production, and the one we don't know how to reproduce. Now, what is the perfect ingredient for that type of bug? And you might have guessed it, it's concurrency. So say hello to curry, that's what I like to name it. And the agenda for this talk we'll be looking at concurrency. What is it? Why are we doing it? We'll be looking at the role of testing in all of this. And then I'll be covering an end-to-end stress testing use case. We look at how to provoke bugs, how to diagnose and debug bugs. And so let's start with what is it? If we ask, Google is not that sure. So there appears to be some confusion in terminology, so let's all get on the same page first. As I would see it, concurrency is the execution of multiple tasks during overlapping time periods. It's the opposite of sequential execution, and what do I mean by this? Take the familiar browser scenario. We're using a browser, opening a website, and then scrolling down immediately. What will the browser do? It will show the text first, then let us scroll down immediately, react instantly, and if there's images on this page that take longer to load, it will do this at the same time. So to us, it would look like it does all the things in parallel. But actually, what might happen is just it's interleaving. It's executing everything on a single thread. And the CPU doesn't need all the time for scrolling. It doesn't need all the time for loading the image. So these can get broken up into pieces and executed in an interleaving fashion. And both of these modes are concurrent, as opposed to sequential. Sequential would mean that loading the text or showing the text first, then loading the image. And at that time, if we wanted to scroll at the same time, the UI would freeze. So what Google tells us is concurrency is hard, and I guess everyone would agree. So why are we doing it anyway? Of course, we want to use CPUs and energy efficiently. We want to proceed reading an article while an image is loading, so we don't want to wait or have the UI freeze waiting for a response from the server. Basically, we don't want to wait ever. So where does concurrency happen? Of course, everyone knows it happens in the backend. We have parallel sessions competing with each other for CPU and resources, accessing the same database and stuff. So everyone knows that one. And now you might think of microservices. And that's true. With microservices, it's even more concurrency. But the considerations for backend sessions also apply to microservices as well. So I won't be covering microservices in this talk. Concurrency doesn't just happen in the backend. It also happens in our frontends because today's frontends are all reactive. And we have interaction events traveling from the UI to the front-end logic. We also have state traveling from the front-end logic to the UI's view models. There's also concurrency between front-end and back-end. If we have event-based systems, we have lots of that. So we have events traveling from the front-end to the back-end, and then events traveling from the back-end to the front-end. And these events could even contradict each other. So concurrency is pretty much everywhere, and it only differs in what type of systems we build. The normal request-response style systems have a lower level of concurrency than these highly concurrent event-based systems. So how do we master it? It takes a number of steps, starting with architecture, building blocks, testing, training, practice. And just keep in mind that with coroutines and structured concurrency, Kotlin brings us real superpowers, making our way to concurrency so much easier. But there's always something to improve. This talk is about testing. So let's look at our testing toolbox. This is the familiar test pyramid. At the low level is unit tests. We're testing individual functions, see, okay, we put something in, let's see what comes back. Does it meet our expectations? Next level is service tests. We use a service, use its API, and see what comes back. Does it meet our expectations? And then at the top, there's the end-to-end UI tests, which is we use a single front end, do some stuff, see what comes back to the front end, and might even do screenshot testing to see whether it looks like. So this is what we conventionally do. Now we could say, why are we using multiple test layers at all? If we look at code coverage, we could easily cover all relevant code with just unit tests, right? So that's not the reason. If we ask GPT for Omni, it would suggest a number of things, among them integration verification, more realistic scenarios, or complex interactions for using multiple test layers. So we could also look at it another way. The Swiss cheese model. No single layer is perfect. Multiple layers catch more bugs. Let's see. Some bugs can be caught by the unit test layer. Other bugs go through the unit test layers but will be caught by service tests. And then even more bugs may be caught by end-to-end tests, not caught by the other two. And so these layers do test concurrency too, right? Well, not quite. This is a simplified attempt to break up concurrency into different dimensions. There's concurrency dimension A in the front end, driving dimension B between front end and back end, and then driving dimension C, concurrency in the back end. In reality, it's even more complex, as front end and back end contain several layers of concurrency each. So if we look at concurrency coverage in our tests, looks like this. Our tests are mostly driven sequentially. So our unit tests use a single function. They won't cover any concurrency layer. The same is actually true with service tests because we test against a single service. No concurrency there regarding these concurrency dimensions. Yeah? And then end-to-end unit test actually may test two of the layers because we use a single front end, then we use the front end back end connection, so we have some concurrency there, and we have the in front end concurrency. So we may cover two layers with these. But this is the maximum we get. We get layers dimension A and dimension B, and as always, terminology varies. So your tests may have a different structure. So if you're doing even more and have concurrency in unit tests, great. If you're using something like lincheck, excellent. But commonly, the dimension we're missing is the entire system concurrency and dimension C in the back end, testing everything driven by the front end over dimension B to dimension C. And then this is what might happen. Our usual defenses catch the usual suspects. But then there's Curry again, managing to escape into production. So what can we do to avoid this? And you might have guessed what comes now, is use end-to-end stress tests. So back to our test pyramid. If we look at complex interaction coverage, then it could actually look this way. Unit tests cover the least complex interactions. Service tests do cover some more, end-to-end UI tests even more, and the most we get is with end-to-end stress tests. The same if we ask the question, to what extent are we covering real-world scenarios? Again, unit tests the least, service more, end-to-end UI tests even more, and end-to-end stress tests the most. Why is that? Because when we're driving this from the front end, we know to predict end-user interactions in real world way better than we can predict the internal API interactions resulting from these end-user interactions. So there are reasons not to do end-to-end tests, right? And I've taken an article from martinfowler.com called The Practical Test Pyramid, written by Ham Bocky, and he's claiming that end-to-end tests are notoriously flaky, they require a lot of maintenance, and they run pretty slowly. So, but as always, these claims depend on a specific context, and the article was based on experience with browser-based tests using Selenium. So, context matters. Let's look at a use case. I have an example app which does collaborative text editing, and relax, the code for everything I'm showing now is available for you on GitHub. So this is our app. We see 4 front ends. The outer ones are desktop front ends. The inner ones are web front ends. And so collaborative text editing, you can edit anywhere, and it will synchronize across all the front ends via the common backend. As you may notice, the front ends are intentionally slow to react. This is to demonstrate eventual consistency and make it a bit harder. So the example app architecture looks like this. We have a JVM backend. We have these desktop front ends which also run on the JVM, and we have browser front ends running on JS. They're connected via WebSockets, and on the backend there's a WebSocket session, one for each front end. So now, if we want to do end-to-end stress testing, that means to execute the entire system under massive load with production-like concurrency. And the entire system in our case looks like this. We have desktop, browsers, the backend, but we have 100 desktops. And we have 900 browsers. So that's our real-life usage scenario. So how would we end-to-end test such a system? Launch 1001 processes? And suppose we did that. If we wanted to debug this, say it runs for 2 hours and then one front end fails, and then we want to set a breakpoint. What would we do? Launch 1001 debuggers? Probably not. So what if we could change the game and integrate all this on a single JVM? Then we could test this massively concurrent system efficiently and debug it like a single backend service. So how can we get there? With Kotlin Multiplatform, let's see. Recap, we have the backend on JVM, we have the front ends on JVM and JS. And to integrate this on a single JVM, with the backend code, it's easy. We're all good because it's already on the JVM. So good here. With the front end, it's a bit different because we have 2 targets. We have JS and JVM. So we need to make sure that both targets share all code. And then we can test on the JVM and be assured that we've covered JS as well. So Kotlin Multiplatform actually makes it easy to achieve this. On the backend, everything JVM only. We're using Ktor as the WebSockets and HTTP server. And on the front ends, we'll be using Ktor client, which also comes with a common API for JS and JVM. For the UI, we can use Compose, also common API, JS and JVM. And basically, that's it. We now have common code across all platforms ready to test on the JVM. Let's see how we get networking from production to testing. With Ktor, it would look like this. Our production server could look like this and be configured by a backend module, which is a simple function we see right now. So the function to configure the server would look like this. We install WebSockets, then we install some routing, which fires up WebSocket sessions. So that's our backend module production code. The production client would look like this. A bit different on JavaScript and the JVM, but not much. Yeah, and let's see how we can replicate all this on our test system. Again, easy with Ktor. We can use Ktor's test application, a standard function, and then configure it with the same backend module function we've been using for production. So we don't need to configure any networking. And we're using the production backend module. The test client can be connected via this test application we just had. And then it can use the same function to launch its WebSocket sessions. Again, no network configuration necessary and almost no code changing. Also, if we want to, we can launch 1,000 clients very quickly that way, as it's all coroutines. We may not want to, because we know normally browsers, for example, each one is running on a single thread. So we might want to have individual threads for that to be more realistic in their timing. So next thing is the UI. Let's look at how we can get Compose from production to testing. We don't want to rely on 1,000 persons operating the UI for us. So we need headless UIs, driven by test code. And with Compose, we actually have two options for that. We could use the test function run compose UI test, which comes with Compose. But we could also use a custom applier, which is basically inventing Compose for a new target platform. Most of us may know Compose UI, which is available on mobile, desktop, and browser on Canvas. But we also have Compose HTML, which is composed with a different API for its composables, driving the DOM. So we deal with CSS and stuff. And we can use something like that, so create something like Compose HTML just for a headless client. Now, in these cases, both of these options would use the normal state management of Compose. They would also use the normal composition functions of Compose, say, updating state, launching effects, and building the UI tree. The differences would be that Run Compose UI tests would do layout, and it would also do drawing and animations, which our custom applier would not need to do because we're only interested in state for the stress test. So let's look at how to build such a custom applier. We basically need to have a class to do the UI tree. And this is basically a tree of view nodes. Pretty simple, number of children per node. And then we have one special node, which is a text node. This is the only one we need for our application. This has content to string. And with this, we can teach Compose how to build an UI tree via just a simple set of functions. So this is actually all we have to use to teach Compose. Nothing more. Next step in the custom applier is we need to do the same as we would when we would move from Compose UI to Compose HTML. We need to convert each composable to use the new view nodes. And this would mean changing the composable to something like this. You don't need to remember the details. You can look it up in the repository if you want to, but remember that it doesn't have to be a large amount of code. We also need some one-time plumbing, like a frame clock and a state observer driving recompositions, but this can be just copy-pasted, for example, from this repository. So when would we prefer which option? Run Compose UI test, of course, provides the complete functionality of Compose, while our custom applier will be pretty fragmentary. Also, the CPU load of Run Compose UI will be much higher because it will be doing layout and drawing, while our custom applier would just be doing state management, so way less. And this could actually be an advantage because remember, we're all integrating this on a single JVM, so maybe we don't want to use the CPU mostly for driving the front end because that would distort the reality of the system. So Run Compose UI test may not be optimal for this. Development effort, of course, is different if you have lots of different composables. it is a higher development effort to build the custom applier and convert each composable. If we use run compose UI test, we can use them as is. And also, a frame clock is there. Run compose UI test uses a skipping frame clock, so it wouldn't do the normal 60 or whatever frames per second for animations and stuff. So this is not as realistic as if we would use a custom applier with a regular frame clock. So what we're using depends on our goals. What do we have so far? We have a single JVM integrating our backend, our headless frontends as much as we like, and with full end-to-end observability because it's all on the same JVM. So we can look at state for all frontends from our test code. We have access to the logic of all frontends. We can look at all backend sessions, the database, whatever is there. So our next step would be to use that system to provoke concurrency bugs. An example is front-end induced update stress. So how can we achieve this? We start 500 frontends, then do mass updates for 3 seconds, so all frontends updating at the same time, and then stop 500 frontends. And then let the test check if everything arrives at the state we expect. So how could we achieve this? Implementing the front-end would look like this. A normal front-end would maybe have a main composable, which launches an effect, for example, to start our front-end production logic. And we could instrument this with a test function, which we could then optionally pass for tests. If we don't use it, the cost and risk in production for this is basically zero, simple null check. But this way we could inject our test function there. So when we want to run the test with something like this, we might be tempted to do it like this. So launch 500 frontends, then call some run frontend function with our test function. But this might not work as expected, because what we want to see is something like this: start the front ends, then have mass updates at the full concurrency level for 3 seconds, and then stop the front end. But instead, what might happen is this. Some front ends start quickly, then immediately start to run their updates, and then stop early. Others start later. The load curve you're seeing here is not precise, but you might get the idea. So with everything mixed up, we lose our focus and never reach the intended update concurrency. So how can we fix this? We need to handle the non-determinism that is there. So suppose we have a way to ask when the front end is ready, like this function. Suppose it is there. The problem is, when we do this initially, it would always return false because it would not be ready initially. It would take some time, and we don't know how long does it take. Compose is asynchronous. But what we could do, for example, with code-test, is using a code-test matcher, which is basically a thing throwing an assertion if the test fails, and then wrap it into an eventually function, which repeats a failing test until it either succeeds or the timeout is reached. So at the end of this function, we can be sure that our front end is guaranteed to be ready. And we could combine this with gates, because we want to start updates only when all of our front ends are ready, not a single one, all of them. So a gate is just a special purpose mutex. We start with a closed gate, then use a test function like this, which would wait at the gate until it opens before starting its updates. And then at the end of this function, where 500 frontends have been started, all are waiting at the gates to open, we can be sure that our frontends are ready, because the launch frontend function guarantees via code test eventually that it would wait on each frontend until it's ready. So at this point, we could just open the gate and let them all run at the same time. And the result is concurrency as we expected, as we want it to be, and not some arbitrary load with some unpredictable results. So we can use eventually in gates to control non-determinism and focus testing on what matters. We can also concentrate stress to provoke concurrency bugs. We can also use nested gates for complex front-end, back-end interactions. And I guess you will find an example of this in the code. I will not touch it here for reasons of time. But there's also some caveats with this. We're using timeouts, and timeouts depends on hardware and load factor. If we use nested gates, they may deadlock. And also, the test code we're using may run on an unexpected thread. So we must make sure that the state we're seeing is really up to date, which might mean we might want to use volatile. And also, we might want to consider synchronization with synchronize, or in multiplatform form, Kotlin's atomic view. So now that we know some techniques to provoke concurrency bugs, let's see how we could diagnose them. And when diagnosing concurrency bugs, we could use our standard instruments, which are stack traces, logging, telemetry, coroutine dumps, and of course, the debugger. Let's see how that works. An example, we have a happy scenario which says, okay, a front end says do, and remember our system, as we've seen it, was just replicating each edit to every other front end, so all arriving at the same state. So now we want to change something. If the front end says do, the backend should change this, not echo, change to done. Yeah, that's what we would expect. Backend should respond with done, and then the front end would detect done, and it's happy. So, and now our presumed concurrency bug could be that the backend sometimes responds with, oh no. Front end would detect that and yeah, be unhappy. So let's look at stack traces in this case. A stack trace would tell us what went wrong and where it was detected. It wouldn't tell us why it happened or where the problem originated. So next, look at logging. And this is just what 4 front ends, 4, produce when a bug happens instantly. So in such a simple case, we might find some hints where the problem originated. But imagine this with 500 front ends running for 2 hours before the bug occurs. So it was way too much. And by the way, telemetry is not that much better with event-based concurrency. So regarding our concurrency bugs, we're still somewhat clueless. Now, what if we could get some focused information about what happened when? We could use logging attached to objects, and that's what I call debug traces. Here, we don't see the intertwined logs of 4 front ends and the back end, but just the focused log lines for the single front end that was detecting the failure. So in this case, we can rule out front-end internal problems like our UI displaying the wrong content, because we clearly see, okay, the front end has got this from the back end. And then the corresponding backend session would look like this. We can see immediately that the backend actually sent the unexpected or no response. So we can now look further why it decided to do that. Using a debug trace is pretty easy. It's almost like standard logging. I use actually a marker interface debug trace target, which then has a nullable property called debug trace. And this properties class provides a log method, which we could use like a standard logger. We also can create a debug trace whenever it's convenient for us. And we can remove it or recreate it at any time if we lose interest in its content. So to avoid memory leaks, debug traces can get big. We should use normal resource management like closable interface and deleting a debug trace in the close method. And the actual implementation of a debug trace is quite straightforward. It's basically a thread-safe mutable list of text lines. And then we store a global map of objects to their debug traces to keep the debug trace overhead away from our production objects. The debug trace property is a simple extension property which is just null when no debug trace has been created for this target object. And there's also a switch to completely disable it in production, so the debug trace overhead in production is basically 0. So instead of logging and telemetry, we can use focus debug traces. Now what if we could get those in addition to stack trace whenever we detect a bug? And CodeTest actually has a solution for the problem that some assertions cannot provide sufficiently meaningful information when a test fails. So this message is not helpful. And CodeTest provides clues for that. So we can add some context information when an assertion fails. And we can combine this way of adding context information with debug traces. So for our test, we might use something like this. We have a test action and wrap it in clues, providing the corresponding front-end debug trace and the corresponding back-end session debug trace. And then the result would look like this. We can see what was detected, where it was detected from the stack trace, which front-end and back-end session was affected, what happened before on the front-end, and what happened before in the corresponding back-end session. So instead of logging telemetry, we use debug traces, then combine this with a stack trace with CodeTest clues, and we could even add coroutine dumps if that helps. And the result is complete focused information about what happened, where was it detected, and what happened before. And with this information, we could use a debugger to dig deeper. Remember, the situation is we have everything, the complete distributed system, on a single JVM, so we have access to all of its components. And we could just debug it like a non-distributed system. So we could use the information gained so far, set breakpoints, and then these are concurrency bugs. They might take a time to appear. So launch all this under the debugger, then go for lunch. So to recap, these are our ingredients for end-to-end stress testing made possible with Kotlin Multiplatform. We can integrate the entire distributed system on a single JVM. We can then connect with Ktor, use Compose Multiplatform for the UI, provoke bugs with Kotlin's eventually and gates, and diagnose with debug trace and CodeTest clues. Finally, use a single debugger for the entire system. So with that, you can extend your toolbox with whatever fits best and squeeze out curry before hitting production. And that's it from me. So I say thank you. Don't forget to vote.